Welcome to this deep dive into one of the most exotic phenomena in condensed matter physics, Majorana modes in nanowires, where we can create half a fermion at each end. Here we have a superconducting nanowire with Majorana-bound states at each end, labeled gamma L and gamma R. These are the exotic half fermions we will explore today. Let's begin by understanding what makes Majorana modes fundamentally different from ordinary particles. In standard quantum mechanics, every particle has a distinct antiparticle. An electron has a positron, a neutrino has an antineutrino. In 1937, Italian physicist Ettore Majorana proposed a radical idea. What if a particle could be its own antiparticle? Mathematically, this means the operator gamma equals its Hermitian conjugate. This is the defining property of a Majorana fermion. For comparison, an electron and positron are distinct particles. They can annihilate each other, but neither is its own antiparticle. A Majorana particle is fundamentally different. It is identical to its own antiparticle. This self-conjugate property leads to remarkable physics. To understand Majorana fermions, we need to start with the Dirac equation and see how Majorana's modification changes everything. A complex fermion operator C can be decomposed into two real components. C equals C1 plus I times C2. We can explicitly write C1 as C plus C dagger over 2 and C2 as C minus C dagger over 2I. These are our Majorana operators. Each Majorana operator is Hermitian. C1 dagger equals C1 and C2 dagger equals C2. They are their own conjugates. This decomposition shows that one complex fermion is equivalent to two Majorana fermions. This is the key to understanding half fermions. Visually, one complex fermion box splits into two Majorana boxes. This splitting is at the heart of why we can spatially separate them in a nanowire. Majorana operators obey special anti-commutation relations that distinguish them from ordinary fermions. The anti-commutator of Majorana operators, Ci and Cj, equals 2 times the Kronecker delta Ij. This differs from the usual fermion algebra. For comparison, complex fermions satisfy the anticommutator of C, and C dagger equals 1. The factor of 2 for Majoranas reflects their self-conjugate nature. Let's ask a question. What happens if we try to create a Majorana particle from the vacuum? When a Majorana operator acts on the vacuum, it does not annihilate it. Instead, C1 acting on the vacuum state is non-zero. This tells us that Majorana operators do not have well-defined particle number. You cannot count Majorana particles like you count electrons. Only when we combine pairs of Majoranas to form complex fermions do we recover states with definite particle number. To see how Majorana modes emerge, let's examine the Kitaev chain, the simplest model that hosts them. The Kitaev chain Hamiltonian has 3 terms: chemical potential mu, hopping amplitude T between sites, and superconducting pairing delta. These 3 ingredients compete to create different phases. The interplay determines whether Majorana modes appear. Here's a lattice representation. Yellow arrows show hopping with amplitude T, while pink arrows show pairing with amplitude delta. Now we decompose each fermion operator Cj into 2 Majorana operators, gamma Ja plus I times gamma Jb. When we enter the topological phase, something remarkable happens. Majorana modes from different sites pair up in an unusual way. In the topological phase, B Majoranas from neighboring sites pair up, but the A Majorana at the left end and B Majorana at the right end remain unpaired. The transition between trivial and topological phases is controlled by the ratio of chemical potential to hopping. The phase transition occurs when the absolute value of chemical potential equals twice the hopping amplitude. Mu equals 2T. This phase diagram shows the trivial phase in pink for mu less than 2T and the topological phase in cyan for mu greater than 2T. At the critical point, the energy gap closes to 0 and then reopens. This gap closing signals the topological phase transition. The bulk energy gap is given by 2 times the square root of delta squared minus mu minus 2T squared. It vanishes exactly at the transition. In the topological phase, the unpaired Majorana modes have exactly 0 energy, a crucial property for their stability. The energy of a Majorana-bound state is exactly zero. This is not an approximation, but an exact result, protected by symmetry. You might wonder, why is the energy exactly zero and not just very small? This is a deep question. The answer is particle-hole symmetry. In a superconductor, creating a particle costs the same energy as creating a hole, forcing Majorana states to zero energy. Particle-hole symmetry means PHP inverse equals minus H, where P is the particle-hole operator. This symmetry pins Majoranas to zero energy. This energy spectrum shows bulk states separated by gap delta, with Majorana-bound states precisely at zero energy in the middle of the gap. Now let's discuss how we actually create these exotic states in the laboratory using semiconductor nanowires. Creating Majorana modes in nanowires requires three key ingredients working together. First, we need superconductivity. We achieve this by placing a semiconductor nanowire on top of a superconducting substrate, usually aluminum. The semiconductor nanowire sits on a superconductor. Cooper pairs tunnel from the superconductor into the nanowire, inducing superconductivity. Second, we need strong spin-orbit coupling. This couples the electron's motion to its spin direction. The Rashba spin-orbit Hamiltonian is alpha times kx sigma y minus ky sigma x, where alpha is the coupling strength and sigma are Pauli matrices. Indium arsenide and indium antimonide nanowires are preferred because they have exceptionally strong spin-orbit coupling, with alpha around 0.2 electron-volt angstrom. Third, we apply an external magnetic field parallel to the nanowire to break time reversal symmetry. The Zeeman term is 1/2 G mu B times magnetic field B times sigma Z, where G is the Landé G factor and mu B is the Bohr magneton. We apply a magnetic field parallel to the nanowire. This field must be strong enough to overcome the superconducting gap. When all three ingredients combine, we can derive an effective theory that captures the essential physics. The Hamiltonian includes kinetic energy with effective mass m star, chemical potential mu, spin orbit term alpha sigma y partial x, and Zeeman energy Vz sigma z. The topological condition requires Zeeman energy Vz to exceed the square root of delta squared plus mu squared. This ensures we enter the topological phase. Let's look at typical experimental parameters used in real devices. The proximity-induced superconducting gap is typically around 0.25 millielectron volts in aluminum-based devices. The spin-orbit coupling strength is about 0.2 electron-volt angstroms in indium arsenide nanowires. The required magnetic field ranges from 0.5 to 2 Tesla, achievable with standard laboratory magnets. Nanowires are typically 1 to 5 micrometers long, much larger than the Majorana localization length. A crucial parameter is the localization length, which determines how far the Majorana mode extends into the nanowire. The Majorana localization length Zg equals h bar times Fermi velocity divided by the superconducting gap delta. Let's calculate a typical value using realistic parameters. With Fermi velocity around 5 times 10 to the 5 meters per second and gap 0.25 millielectron volts. This gives a localization length of approximately 200 nanometers, much smaller than the typical nanowire length. The Majorana wave function decays exponentially from each end over the localization length Xi-m, shown here by the decreasing bar heights. How do experimentalists detect Majorana modes? Several key signatures provide evidence. The most famous signature is a zero-bias conductance peak when measuring differential conductance versus voltage. When voltage is swept, a sharp peak in conductance appears at zero bias, indicating the presence of a zero-energy state. The quantized zero-bias conductance is exactly 2e squared over h, twice the conductance quantum, due to perfect Andreev reflection. As the nanowire length decreases, Majorana modes at opposite ends begin to overlap, splitting the zero-bias peak. The energy splitting delta E is proportional to exponential of minus nanowire length L divided by localization length. This exponential protection is crucial. Another signature is oscillations in the zero-bias peak height as magnetic field is varied, matching topological phase boundary predictions. Perhaps the most exotic property of Majorana modes is their non-Abelian exchange statistics. In quantum mechanics, exchanging identical particles produces a phase factor. For bosons, it's +1. For fermions, -1. But Majorana modes follow non-Abelian statistics. Exchanging them rotates the quantum state in a higher dimensional Hilbert space. After braiding Majoranas, the state transforms as psi goes to U times psi, where U is a unitary matrix, not just a phase. Here we see a space-time diagram of two Majorana modes being braided. Their world lines wind around each other, implementing a quantum gate. The explicit form of the braiding matrix depends on which Majoranas we exchange. The braiding matrix is Uij equals exponential of theta times gamma I times gamma j, where theta is typically pi over 4. Non-Abelian statistics makes Majoranas ideal for topological quantum computing, where information is protected by topology. In conventional quantum computers, qubits are extremely sensitive to local environmental noise and decoherence. Topological qubits encode information in the global properties of Majorana modes, making them inherently protected from local perturbations. A qubit is encoded in the joint state of two nanowires. The state 0 and state 1 correspond to different fermion parities across the Majorana pairs. Two Majoranas from different wires combine to form a complex fermion operator C equals gamma 1 plus I gamma 2. The qubit computational basis corresponds to the occupancy of this non-local fermion, empty for 0, occupied for 1. Quantum gates are implemented by physically moving Majoranas around each other, braiding their world lines in spacetime. Despite progress, realizing robust Majorana-based quantum computing faces significant challenges. Real nanowires have disorder, impurities, and inhomogeneous potential landscapes that can create spurious zero-bias peaks. Andreev-bound states and other trivial zero-energy states can mimic Majorana signatures, making definitive identification difficult. Even if Majoranas are topologically protected, they still interact with their environment, limiting coherence times. Moving from demonstrating individual Majoranas to building arrays of interconnected qubits presents enormous engineering challenges. Progress map. Signatures are well established, topological protection is partially demonstrated, but fault-tolerant computing remains an open question. Besides nanowires, researchers are exploring alternative platforms for hosting Majorana modes. Three-dimensional topological insulators with superconducting proximity can host Majorana modes on their surfaces. Chains of magnetic atoms on iron-based superconductors create effective one-dimensional topological systems. Combining quantum Hall edge states with superconductivity provides another route to Majorana physics. Arrays of Josephson junctions can simulate topological superconductors in a highly controlled manner. These platforms offer promising alternatives for discovering and studying Majorana fermions.